In 1859, a quiet, reserved German mathematician gave a lecture upon his admission to the Berlin Academy of Sciences. At the request of his mentor, Bernard Riemann spoke on number theory and the distribution of the primes. In his quest to find a pattern to that distribution, he dusted off an obscure function, reformulated it in the setting of complex numbers, and discovered a fascinating connection between this function and the distribution of the primes. However, there was one property that Riemann believed this function possessed, but he could not prove. 150 years later, we still can't. This property is known today as the Riemann hypothesis.
Formally stated, the Riemann hypothesis is all non-trivial complex zeros of the zeta function have the form s equals 1/2 plus bi. To unravel this statement, we must ask, what are complex numbers, what is a zeta function, why are its zeros so hard to find, and what connection does this function have to the distribution of primes? In high school and college algebra, we are introduced to several types of functions and learn techniques to study their properties. We begin with the simplest functions, lines and parabolas, and then move on to higher degree polynomials and rational functions. These are our common algebraic functions. Later, one encounters exponential and logarithmic functions. If your coursework included trigonometry, you studied periodic functions like sine, cosine, and tangent. These functions are said to have a closed form expression, a description that can be written in terms of a few elementary functions. The zeta function does not have this property. It is based on an infinite series, a never-ending sum of terms involving the variable x. An infinite series can be an endless repetition of the same term or have terms that change according to their position within the series. If you have seen an infinite series, it probably occurred in a second semester calculus course where one studies power series and learns various tests for series convergence. A power series is the most common type of series and can be thought of as an infinite polynomial. Many common functions have a power series representation. Even polynomials can be viewed as a power series if we assume a zero coefficient on all the high degree terms. The Taylor series representations for sine, cosine, and e to the x are given. These series representations are valid for all real numbers. A series representation for the logarithm function is also given. However, the series matches the function value only when x lies between -1 and 1. Although the log function is defined for all real numbers less than 1, if the value is less than -1, the series is useless. The geometric series is another example of a function with a finite interval of convergence. The rational function f of x equals 1 over 1 minus x can take on all real numbers except x equals 1. However, the series only matches the value of the fraction whenever x lies between -1 and 1, the same interval of convergence as the log function. Using x equals 1/2 as an input, the fraction on the left-hand side simplifies to 2. The values of the series are determined by a technique called partial fractions. In it, we successively add to the previous sum to generate a sequence and analyze its behavior. Using x equals 1/2, the first term is 1. The first and second terms in the sum add up to 1.5. The first three in the series add up to 1.75, the first four to 1.875, and so on. As we add more terms, these truncated sums get closer and closer to the value of 2. In this case, the series converges to 2. When we input values of x outside this interval, we lose this nice behavior. The choice of x equals 3 creates a left-hand side of -1/2, but the partial sums for the right-hand side increase without bound. The choice of x equals -4 creates a left-hand side of 1/5, but the partial sums alternate between progressively larger positive and smaller negative numbers. In both situations, the series diverges and provides no useful information. There are also functions that are defined by a power series but do not have a closed form. One example is the zero-order Bessel function, which arises as a solution to a specific differential equation. Its expression cannot be represented in terms of polynomials, exponentials, logs, or trigonometric functions. Its graph looks like a stretched out, damped cosine curve. The zeta function begins with a similar series. It is defined as the sum from 1 to infinity of the reciprocals of each natural number raised to the x power. The series will converge to a finite value as long as x is greater than 1, otherwise the series diverges. As examples, if x equals 2 is inputted, the series converges to pi squared over 6. But if x equals 0 or x equals 1 is chosen, the series diverges. X equals 1 yields the well-known harmonic series.
A few mathematicians had studied the zeta function prior to Riemann, but they were primarily interested in deriving some useful identities. To that extent, they had only considered the function as being over the integers or possibly over the reals. However, in the previous decade, Riemann had studied the complex numbers extensively and developed much of the field that we now know as complex analysis. So he decided to reconsider the zeta function as a function over C and study its properties. What he found was nothing short of amazing.
Complex numbers are an extension of the reals. Standard multiplication rules state that there is no real number that you can square and return a negative value. So we created one that does. We define I to be the square root of -1 and call it imaginary since it is not a real number. We define the complex plane to be the set of numbers of the form s equals a plus bi, where a and b are real. Modern texts use z for the complex variable, but s was the common usage in Riemann's time, so it is kept when discussing this problem out of respect for him. Complex numbers are visualized as points on a plane, with the horizontal x-axis representing the real part of a complex number and the vertical y-axis representing the imaginary part. Complex numbers and complex functions have their own arithmetic, algebra, and calculus, most of which parallels operations on the reals. Unfortunately, complex functions are impossible to fully graph since that would require 4 dimensions. However, complex functions in general have many nice properties that real functions do not possess. Depending on a given problem, the lack of visualization may well be worth the trade-off for better behavior. One of these nice properties is analytic continuation. If a complex function is analytic, or particularly well behaved, on a specific region, it can be uniquely extended to a function that is well behaved on the entire complex plane, except for possibly a specific number of points called poles. This is somewhat like a child function defined on a small set that extends to a parent function defined on a larger set. This is not true for real functions in general. We have already seen a few examples of analytic continuation. Since the real numbers form a subset of the complex numbers, functions like s squared and tangent s are continuations of the functions x squared and tangent x from R into C. The rational function 1 over 1 minus x is a continuation of the geometric series, extending the series from the interval -1, 1 to all of R except for x equals 1. For those with no formal training in analysis, the analytic continuation of the zeta function may appear quite daunting. However, certain characteristics are worth noting. We begin with the series. Over R, the series is defined for all x values that are greater than 1. Over C, it is defined for all complex numbers in the right half plane whose real part is greater than 1. Using some tricks from analysis, it is possible to find a formula that defines the zeta function for the complex numbers in the strip with real part between 0 and 1, except for the specific value of s equals 1, which yields the harmonic series. For the complex numbers in the left half plane, whose real part is less than 0, Riemann devised a functional equation. This particular identity connects the function values at s to those at 1 minus s via 4 other terms. two exponentials, a cosine term, and the gamma function. The key to this equation is that all four of those functions have known values. So if the real part of s is less than 0, then the real part of 1 minus s is greater than 1, and the right-hand side can be evaluated using the zeta function values that are already known. This functional equation also suggests a symmetry of the zeta function about the line a equals 1/2. Together, these three parts define Riemann's zeta function for all complex numbers except s equals 1. At s equals 1, the function is undefined since it takes on an infinite value. Zeros, or roots of a function, are the input values that return an output value of 0. In algebra, the zeros are found by setting the equation equal to 0 and solving for x using techniques such as factoring, the quadratic formula, and completing the square. For real functions, the zeros are also the x-intercepts, or the place where the function crosses the x-axis. A pole is a point at which the function takes on an infinite value. For real functions, poles or singularities are called vertical asymptotes. A function may have no zeros, a few zeros, or infinitely many zeros depending upon its type and other properties. Using the analytic continuation, we can separate the complex numbers into three regions. For the first region, where a is greater than 1, the zeta function has no zeros. For the third region, where a is less than 0, zeta is defined by the functional equation. For this functional equation, the right-hand side only has zeros whenever the cosine term is 0. For these values, that means s must be a negative even integer, such as -2, -4, or -6. These values are called the trivial zeros. That leaves the middle strip. Finding the zeros in this section is not quite so obvious, and there is no explicit formula to do it. Riemann calculated the first few zeros by hand and found that they all lie on the line of symmetry a equals 1/2. He believed that all of the zeros lay on this line, but he couldn't prove it. That statement has become the Riemann hypothesis. So what connection does this function and its zeros have to the distribution of the primes? Prime numbers are whole numbers that are divisible only by themselves in 1. They start with 2 and include the numbers 3, 5, 7, 11, 13, 17, and so on and so forth. They are considered the building blocks of the integers and have been studied since the introduction of multiplication. The ancient Greeks were able to show that the list of primes goes on forever. We also know that they get farther and farther apart, but we don't know a lot about them in general. We don't know if there is a special formula that would generate all of the primes. We don't know if there is a regularity to their spacing. By 1800, the theoretical and empirical evidence both suggested that there was no set formula or regular spacing, so emphasis shifted instead to looking for probabilistic distributions. So given a range of numbers, can we determine how many primes lie within that range? In the early 1800s, Carl Friedrich Gauss proposed the prime number theorem. The function pi of x counts all of the prime numbers up to and including x. His theorem states that for any integer x, the number of primes less than or equal to x is roughly equal to the ratio of that number to its logarithm. Furthermore, the larger x gets, the better that approximation is. As x increases, the discrepancy between the actual number of primes and pi of x still increases, but it does so at a fairly slow rate. Shortly after, Peter Dirichlet derived an alternative form of the theorem using the logarithmic integral. The two forms are mathematically equivalent, but the logarithmic integral provides a slightly sharper approximation. In either form, the expression provides an approximation for pi of x, but not an exact value. Riemann did not prove the prime number theorem, but found a formula that would express the error in Gauss's approximation. The series of the zeta function was originally studied by Leonhard Euler in the 1700s. In 1740, Euler discovered an interesting property. He was able to rewrite the series as a product of terms involving the prime numbers. This identity is now called the Euler product in his honor, and it provides a direct connection between the integers and the primes. For those interested, the internet currently houses several videos that explain how one can obtain this identity.
Once Riemann applied the tools of complex analysis to the zeta function, a whole new world opened up at his fingertips. His advances were astounding. This is an overview of his process.
First, he created a variation of the pi function, which I denote by psi. This function counts not only the primes but all powers of primes. In it, the first term counts all the primes. The second counts the squares of primes, such as 4, 9, and 25. The third counts the cubes of primes, such as 8, 27, and 125. In such a fashion, each prime power is counted. Second, Riemann used the Euler product and its properties of logarithms to establish a relationship between the psi function and the log of the zeta function. Third, using complex analysis, he could express psi explicitly in terms of the zeros and the poles of the zeta function. Finally, he used inverse transforms to reconstruct the original pi function from psi. This is a brilliant connection of seemingly unrelated ideas, and if the zeros are known, his formula gives an exact value for the quantity of primes in any given range of numbers. In his 1859 paper, Riemann stated that he believed all non-trivial zeros of the zeta function have a real part equal to 1/2, but he couldn't prove it. For his research, the proof was unnecessary, so he didn't pursue it, and he never wrote on number theory again. For us, his passing remark has now become the most famous open problem in mathematics. Although no one has yet proved or disproved this statement, progress has been made. Many people have tackled this problem from various angles. So far, every non-trivial zero that has been computed does indeed lie on the critical line. At present, this is over 10 to the 13th zeros. We also know that at least 40% of the non-trivial zeros lie on this line, and that an infinite number of the zeros lie on the line. We also know that most of the zeros are mathematically close to the critical line. However, none of these results guarantee that all of the zeros lie on the line. We only know that any zeros that don't lie on the line must be really, really big and really, really rare. The validity of the Riemann hypothesis has far-reaching consequences. Many theorems in number theory begin with the statement, if the Riemann hypothesis is true. Certainly all these theorems would be proven. They include, but are not limited to, other questions regarding the distribution and frequency of the primes, tests for primality of a number, and counting functions for other kinds of numbers. There are also analogues to the zeta function and its corresponding Riemann hypothesis in other areas of mathematics, such as ring theory, field theory, and algebraic geometry. In the past century, connections have also been made between the zeros of the zeta function and both probability distributions and energy levels for chaotic systems in quantum mechanics. A proof of the Riemann hypothesis could strengthen research among these fields. Finally, a valid proof of the Riemann hypothesis could affect all of us directly. Most public key encryptions depend upon the inability of computers to quickly factor multiples of very large primes. If true, the exact number of primes would be known and tables of primes could be constructed and used to infiltrate internet security protocols.
The general consensus is that the Riemann hypothesis is true. It has good empirical support, good theoretical support, and a number of elegant results cascade from it. Intuitively, most number theorists sense that it ought to be true. However, at present, we either lack the tools sufficient to tackle the problem or the proper insight to use the ones that we have. So if you like algebra, like analysis, and have time on your hands, you too can try your luck at proving his hypothesis. You just might win $1 million prize.